So, well, that's too bad because I think this is when we're going to actually do full-blown electrodynamics. So in preparation for that, I want to talk about energy stored in a magnetic field. We have seen something before. What is the energy stored in an electric field? So energy density, I think we used U, right? Or did we, right, or the, it was 1/2 epsilon naught E squared d tau, okay? So we can expect, this is, of course, energy in an electric field. So we can, and it's never a good idea to just expect, but we know when we know the answer, you know energy is 1/2 mv squared or something like that. So there's got to be a 1/2. There's got to be a v squared d tau. Instead of epsilon naught, what do you expect? Yeah, except it's in the denominator, just how the symbols work out. So this is where we're headed towards. Okay, so I mean, you really cannot expect mu naught. You would, if anything, you might expect it here, but we'll just see how the story.
When we had is Q over epsilon naught versus mu naught unenclosed. You know, those are.
Well, yeah. So.
If anything, it's consistent with.
Right. That is true. Good. So it is indeed expected. So suppose you have a circuit, right? And you might have, you know, what are the components we've talked about so far? Maybe a resistor, maybe a capacitor, and you know, maybe multiple things of this nature. Okay? And when you have a current running through the circuit, of course the resistor gets heated up and energy is lost. That is not what we're talking about. We have seen that. It's I squared RT, right? We're not talking about that. But there is a back EMF. To sustain the current, you have to find the back EMF, okay? So when you have an EMF, you have to supply an induced EMF. You have to supply opposite to that. So work done is equal to, well, first of all, it is minus E, right? But this is not quite true because this is EMF, that is energy per unit charge. Yeah? So I can fix this and make it an exact equation by doing this rate of change. I'm going to erase, so don't write down. Okay, so let me do it this way. Don't write it. I'll clean this up. So this is work done. This is the work done per unit charge. So maybe the total charge. Yeah? We have no idea what that is. So what we can do is we can do that. And then we can do that. This is great because this is the current. Yeah? So and this is the version. You also know that this is minus Li. Correct? So then, what's that?
Yeah.
Yeah. I mean, if there are other parts. There might be other inductions, but we're not. I wonder if Griffiths gave a diagram. I don't think. I don't think he did. Okay. So then. dw dt is, hold on, I'm missing a derivative. The EMF is minus, correct, and it's L, let me make sure. Yeah, that's where I made the mistake. It's a rate of change. Yeah? It's the flux that is equal to Li. But the EMF, it's a rate of change of that. So then this becomes Li di dt. A little bit of simplification is what? D dt of 1/2, L is a constant, Li squared. Because what's the derivative of I squared? 2I di dt. And the 2 would cancel with 1/2, and you would get this expression. So the derivatives of this are equal, so and when the current is 0, you don't have to fight it, so you can directly argue that this is in fact true. Again, I like this expression. It has that 1/2 mv squared kind of look to it. So very often, inductance is difficult to calculate. But if you have a way of computing W and the current, the work, the energy stored through the magnetic field, at the end of the day, it's going to come out of this formula. And the current, this could be a prescription for inductance as well. So put that as a note. Indirectly. You know, first of all, we computed L only for a loop. But what happens if you have a volume current? Yeah, it needs more advanced techniques that we're not discussing, but we can directly use this formula. Okay, so we're going to do a little bit of playing around with figures. Okay, so the magnetic flux is equal to what? Well, on one hand, it is Li. But that's equal to B dot dA. Correct? And that's equal to curl of A dot dA. So again, within the context of what we're doing, so you have a loop, and then you compute the B dot dA, and you get, so again, using Stokes' theorem, this is nothing more than now A dot dL. Correct? All right. We know what this is and where we're headed. So we now get work is equal to 1/2 Li times I, which is 1/2 AI A dot dl. You know, we've done this before. A dot, I can write this as di, but with a vector. L times I times dl is di, because current also flows along the direction of the loop. So this is good if we have only loops. But in general, we have volume current. So from this, I can easily, so I want to say for volume current densities, because this is the most general. From volume current, you can get line current by using delta functions. So volume current is the most general case. I can write this as A dot di is being replaced by J d tau. Yeah? Okay. So now, there's a little bit of cheat here, but at the moment I won't tell you where the cheat is. I'll tell you a couple of weeks down the road. Correct. So, tell me why I can do this. First of all, look, I get my mu 0. And tell me why. It's not difficult. What did I do? Replace J with del cross B over. So that means in this in this development, I'm assuming what? Well, something we think we know, which is del cross B. Yeah? Okay, fine. So now I want to do a little bit of algebraic shuffle. So the divergence of A cross B, and I'm going to look at the inside cover. Instead of looking at the inside cover, I'm just going to write it down from Griffiths. I mean, otherwise I'll have to go somewhere over here. But it turns out it is nothing but B dot del cross A minus A dot del cross B. That is just a vector identity. So I have an expression for this.
All the variable names work out as well.
I'm sorry?
That all the variable names for the generic.
Right.
work out as
Yeah.
well.
It's where notation is perfectly synchronized. Almost never happens, right?
Yeah.
A and B just means exactly A and B. So help me to not make a mistake. This guy is going to be this minus that, correct? So I'll get two terms. One is B, and I'm going to just do it this way, it doesn't hurt. I don't want to skip too many steps. This is over wherever there's B and A, right? Minus divergence of A cross B. Of course, this is a place only where J is non-zero. But if you might as well integrate over a larger space, because if you have a larger space, del cross B outside of where J is non-zero is going to be, outside of where it's going to be zero is going to be zero. So this will not contribute to anything. So you can integrate through all space, or any region if you're so interested in. And there you effectively get what you want, which is there. B squared, B dot B is B squared. No longer, B dot B is what I mean by B squared. And I can use Stokes' theorem, divergence theorem, and then do A cross B dot dA on the boundary. If you include all space, the boundary is infinitely far away. So the A and B will go to zero. So we can have and that's precisely how. So this is the magnetic energy. This is great, it's effective. It's one way to discuss this very clearly without doing a more complicated topic, which has got to do with energy and momentum of a field. There's a way to construct an energy momentum tensor, and we will. And then you can backtrack and see that this is in fact the answer. But Griffiths didn't want to wait till the end of chapter 8, or maybe the beginning of chapter 8, to actually have this conversation. That is why he quickly derived this using just a circuit conversation, and then he generalized it to a volume, and he quickly got to a result because A, it is quick, and it's important, it's intuitive, and it's fast. And we don't have to worry about all the unnecessary mathematical complications. But remember, how you maintain a current in a circuit is not the comprehensive discussion about energy stored in a field. Because it's a circuit, what happens if you have a sheet, what happens if you have a volume, and what happens when current is not perfectly defined like in a loop. Yeah, so there's a little bit of sleight of hand. But with the conversational ease, he'll never let you know about that portion that he has not discussed. So, and Griffiths is very good at this. You have to be careful of his Jedi mind trick. He'll just let you go, well, all of that is very clear. It is clear. It is not untrue, but there's a larger picture there, and we will get to tackle this as well. Okay, let's do a problem to use this. So I'll just pick a homework problem. I mean, the problem in the back that illustrates this, and where the calculation is not so difficult. So the problem I'm going to do is problem 730. A long cable, okay, so you have, of course this is infinitely long, cable, and there's a current, uniform current, J. Okay, uniformly. And the current returns along the surface. So, and then he says, basically he wants to shield it from the outside. So there's a thin, this wire is covered by a thin sheath, and the same current returns. So what goes up is coming down. And the question, so what is the problem that we're trying to do? Find the self-inductance. Remember, I told you you get to use the energy stored formula to compute the inductance. Because these are volume currents. How do you find this? Who knows? Fine. But the point is, what's B outside here? Well, B dot dl is mu 0 I, but what's going up is coming back down. 0, 0. And what's inside? Well, it's given by Ampere's law. Okay, so to compute that, I will do B dot dl and pick an Amperian loop. And I get that to be mu 0 times I enclosed. And because of axial symmetry, I just get B phi times 2 pi s. Mu 0, I enclosed is not all of the current. It's only the current in my Amperian loop of radius s. So this one has radius, you can quite see it, I'm marking s. So I need the current through only this portion of the loop. Yeah? Well, that's okay. So that's the ratio of the total area divided by the area of the loop. And so it is pi s squared over pi r squared. Yeah? And so tell me what, so this will go away. This s will give me 1s. So B inside is mu 0 I s over 2 pi r squared phi hat. Did I do my algebra right? Mu 0 I s 2 pi r squared. Yeah? Okay, so then the energy stored in this magnetic field is 1 over 2 mu 0. And I'm going to pick the length to be L. As a matter of fact, the whole length is infinity. So what I can do is not tell you the inductance, but rather inductance per unit length. B squared, mu 0 squared, I squared over 4 pi squared r to the 4th. Oh, this is I squared. Then I have s squared. What's my volume integral in cylindrical coordinates? I have ds, then I have s d phi dz. So I have one of the mu zeros would cancel, I squared over 8 pi squared r to the 4th. This is going to give me a 2 pi, and this is going to give me an L. So times 2 pi L. Then I have s cubed ds 0 to r. Yeah? I'll tell you, right or wrong, I'm already happy. Because W equals 1/2 L I squared. There's the I squared. So let me do it this way. I'm going to do 1/2 I squared. And then what do I have? Mu 0 L. I brought this, so it becomes a 4. So please tell me if I'm doing this correct. 2 pi r to the 4th. See, this is a 4, but I want a 2 here, so I only have 2. One of the pi's cancel, then r to the 4th, and over here I would get r to the 4th over 4. And whatever is in the bracket is the inductance. Notice it doesn't depend on the radius of the wire. So the meaning for quantity, I'm just going to do inductance per unit length. All this B assumes nice axial symmetry and whatnot. It has to be an infinite wire. Is what? Mu 0 over 8 pi. That looks too good to be true. Fingers crossed. Yeah. Again, things like inductance, like capacitance, it only depends on the geometry and parameter of the problem. And at least that feature is retained. Any questions?
Seems like a very simple answer for volume.
Well, okay. Modulo algebraic error, that is the answer.
Yeah.
I don't think we're doing anything wrong conceptually. Okay, but I think that is the answer. We have spent a long while thinking we'll know electrodynamics, and we've waited patiently. So what is the current status as of today? Let's see if you remember this.
Still 0.
Still 0. It would have been 0, but Faraday came in and said, wait a minute, there is induction. Divergence of E. Rho over epsilon naught. And the curve of B is 0, J. Okay, so immediately you'll see there's one problem. See, if I take the divergence of curve, what should I get? 0. Note, divergence of the curve is equal to, well, minus d dt, the divergence of B, partial derivatives can be taken in any order. Divergence of B is 0, so okay. Another thing to note, it's recall. The continuity equation. Divergence of time before space. This is what, this is the continuity equation. So Maxwell didn't have to do much. He just knew how to take divergence and curl like crazy. You have to remember, at that point, that was pretty trendy work. And this is not true. Well, in fact, this is equal to minus mu 0 d rho dt. So this is not 0. Not 0 in general. And looking at this, Maxwell knew exactly how to fix it. Okay, so is that the problem? I can make everything consistent. So what I'm going to do is I'm going to do this. B equals mu 0 j plus, well, I don't know if you wanted mu 0 separate. It looks like you would want mu 0 separately. I hope this is correct. And he said he's going to create a new current called displacement current. Density. Now, what is the job of this guy?
Offset.
To offset that. So then he said, 0 is what I want. Oh, I can even do this. Mu 0 divergence of J plus JD, which is equal to mu 0 times minus d rho dt plus divergence of JD. You just have to solve for JD. It seems a little bit tricky, but it's not. So, divergence of JD should be equal to what? D rho dt. We said, oh, but that is easy because I can write this as divergence of E over epsilon naught. And I know partial derivatives can go back and forth, so I'm going to do 1 over epsilon naught divergence of dE dt. Well, then I just have to compare. I don't have to look at nature. You know, I'm a theoretical physicist. Nature will have to follow this. Look, JD is equal to 1 over epsilon naught a time variant electric field is creating an effective current, a contribution to Maxwell's equations. Except I got it wrong. That is not what JD is. Ah. No, I mean, divergence of E is rho over epsilon naught, so rho is epsilon naught times. Well, that's why it's called Maxwell's equations and not Govin's equations. James Clerk Maxwell is buried right next to Newton for this and many other things he has done. And so, looking at this, for consistency, all he had to do and this is the complete story. This is Maxwell's equations. Yeah? Epsilon naught. This is in vacuum. We'll look at how it behaves in a medium as well. Just for today, it's not very important because I'll do one example to clarify that. The displacement current is epsilon naught dE dt. Do not put this in this category, huh? But what is also important along with this is the fact that the force, the Lorentz equation, the force on a charge is QE plus so we have, in some sense, seen the set of equations that describes a field theory, theory of electric and magnetic fields. It's a great example. All the other fields we have learned, studied about, came through because the insights. This has all the good features and all the problems. There are 3 E's and 3 B's, but there are only 2 kinds of photons. So somehow, these quantities are unnecessary. But we don't know an elegant way of writing this where those quantities can be removed. Turns out you don't need to. This gave birth to a field called gauge theory. In fact, it was gauge theory that taught us how to calculate other forces, the nuclear forces and the strong and weak nuclear forces. Einstein independently discovered the other, we think the last one, unless there's a 5th force, on gravity. It wasn't immediately seen as a gauge theory, but now we fully understand it as a gauge theory as well. So gauge theory is the redundant quantities we have in trying to describe phenomena. Okay. And we'll slowly unpack all of that depending on the time. Well, we'll have time enough for a couple of things. As a matter of fact, I want to do one example that really shows the need for this equation. So this was done just by sort of algebraically manipulating things. So let's look at a simple case of charging a capacitor. It's a standard example. You may have seen it even in your freshman physics book. So you have a battery, you have a current flowing through it. And let's work with the old equation. Yeah? Suppose this displacement current didn't exist. You will get an inconsistency. So I'm going to pick an Amperian loop, and then I do B dot dl. Well, where does B dot dl come from? It comes from, well, curl of B dot dA, that is mu naught J dot dA, which is mu naught I enclosed. Yeah, fine. B dot dl is taking B dot dl over here. Yeah? It's a closed loop, despite how I've drawn it. It is one number. It shouldn't depend on anything else. It's just a number it should give you. Fine. But I have dA. I can pick any area for which this is the boundary. One choice I have is this area. And if I do that, so let me call this 1. For area 1, B dot dl. Well, through here I have this current I passing, so it's just mu 0 I. Yeah? But then it's a capacitor, so I can precisely go a little longer. I can pick this sort of a curved surface area. Well, there's no current impinging this area, is there? This can't be. But if I now put I would get plus mu naught, JD, there it is, epsilon naught, dE dt, the area. I can bring out mu, mu naught, epsilon naught, d dt, E dot dA. But there's electric field here. Correct? This is E dot dA is, what is it? Q over epsilon naught. Charge Q of this plate. Q over epsilon naught. Epsilon naught cancel, and indeed I would get mu 0 I, thereby saving the equation. Because it's one loop. This loop has many areas. So if I do B dot dl, I have to get the same area using any area I want. I can pick the obvious one, and clearly the other obvious one, because that's why we created a capacitor that breaks the current to make the point clear.
When we say like it impinges it, say our little sphere was just bounded inside a thing, it would still, that would be considered impinging because it'd go through.
Right, you mean if it went like
Yeah,
this?
yeah, okay.
Yeah. But we picked it so that
So
it
there's
doesn't
internal,
impinge it.
yeah.
Yeah, so this current is gone.
Mm-hmm.
So the contribution has to be from the displaced current. Yeah? So there we have it, Maxwell's equation describing all of nature. Yeah? And field theory is born. Okay, good.